Section 8.2 is series, and this is our section where we define a series and the convergence of a series. So if we look at the first box on the page, we've got sigma notation. This is read as for n equals 1, we add the term a sub n up to capital N. So in other words, we'll start at n equals 1 down here. We write a1, and then plus we increment n by 1 and add a2, and then increment n by 1 and add a3, and so on until we reach capital N, which is our stopping point in the index, and that's our last term in the sum. So that's the sum of the first capital N terms of a sequence A1 through AN. So a series is a sum of sequence terms. We might think of it that way, or it's a sequence whose terms are added up. We can do the same for an infinite series. Since there are infinitely many integers, we could let our stopping point be infinity. In other words, there is no stopping point. So we'll add a1, a2, up to some a sub n generally, and we just continue onward. So long as our general rule makes sense to do so, we can write down that sum to feasibly sum up infinitely many terms. This is the most important version of this. We'll see a couple examples of summing up to this finite number of terms, but mostly we're going to deal with infinite series as we see below. So we'll get to the idea of convergence of one of these in just a moment. But first, let's make a conjecture about this. So what we want to think about is whether or not we can add up infinitely many terms and come up with a real number, some finite amount. So clearly the sum of finitely many values is a real number. Okay, but it's a little less clear for infinitely many numbers. If we add up infinitely many numbers, will we get some finite real number out of it? Surprisingly, yes, and actually, surprisingly, it's true in a lot of cases. And we'll have to much of this chapter and the next coming sections are to learn about when these things converge and when they don't. So the first one we consider is this: n equals 1 to infinity, and the sum is n. Our general rule is n. So when n equals 1, we get 1. When n equals 2, we add 2, then 3, then 4. Clearly, this is going to diverge, right? We're only adding larger and larger integers, positive integers, and we're never going to run out. So this intuitively we can accept as being a divergent series. Now we haven't precisely defined divergence or convergence, but I think we can see that this sum is going to run off and grow uncontrollably large. Okay, 1 over 2 to the n is our series term. We start at n equals 1, and we're raising this to the nth power. 1/2 to the nth power, n equals 1, and we got 1/2 for the first one. Then we have 1/2 squared, then 1/2 cubed, then 1/2 to the 4th, and so on. Now, if we write down some of these terms, let's consider this down below. Bottom of the page, we have an example of this. Let's get in a little bit more closely to this. And we'll add more general rules in the future, but this is just to work with some intuition. Here we are dealing with that same series, 1/2 to the nth power. And let's look at its partial sums. In other words, let's look at the sum of the first one term. Well, that's just one term, so it's 1/2. The second partial sum is the sum of the first two terms. The index here tells me to sum up the first two terms. When I do that, I get 3/4. Also, s sub 3, the third partial sum, is 7/8. 7/8. Once we add up the first three terms, when we add up the first four terms, we get 15/16. Of course, the details aren't written in here, but the viewer can check those on their own. And really what we can conjecture is that s sub n, the nth partial sum, is equal 2 to the n minus 1. So here if we look, 2 to the 4th is 16, minus 1 is 15. And then divided by 2 to the n, which is, in this case, when n is 4, 16. So we've got 15 over 16 in this case, and this works for all the previous cases as well. Now, if we simplify this rational expression, we get 1 minus 1 over 2 to the n, And if we said, well, we're going to have infinitely many of these partial sums as n runs off to infinity, what do these things look like? Well, we'd see that this term 1 over 2 to the n is driven to 0 as n goes to infinity. So that leaves only the 1. And it looks like overall, this sequence of partial sums goes to 1 as n goes to infinity. So we just sort of established a nice definition for convergence of these partial sums. And in fact, if we were to write these terms down up above here, if we were to look at more of these series terms, write out 1 over 32 and continue to add more and more of the next terms to come on this series, we'd see that we're converging to 1. We're never going to go above 1, and we're going to slow down as we get to it. So this is actually a convergent series. And we'll see more explicitly why without the analysis below once we have the definition and we look at what's called the geometric series on the next page. One more example, the sum of the same series except the series term does not have that exponent of n. So we're just going to add up 1/2. And well, if we add up 1/2 consecutively, the first partial sum is 1. The second partial sum is 1/2 plus 1/2. Oh, sorry, the first partial sum is 1/2. The second partial sum is 1/2 plus 1/2. So that's 1. Add a half for the third partial sum, 1.5. 2 at the fourth partial sum, 5.5 for the fifth, and so on. Okay, so it looks like this one just runs off to infinity, and in fact it does. If we add up infinitely many 1/2s, then we're going to have an arbitrarily large number. Okay, so this is our most important definition in really all of chapter 8. So the definition of a convergent series. So we let S be an infinite series with term a sub n equals 1 to infinity. We define the partial sum S sub capital N as follows. Lowercase n equals 1 up to capital N, our stopping point, and sum up the terms a sub n. So it's exactly what we did below for each of these terms of this geometric series that I talked about. But now it's formalized for any series. And this is our nth partial sum. This lets us define convergence of a series. So what we noticed is that with each of these partial sums, we got a term. Well, these terms come in an order, 1, 2, 3, 4, so on. Right? So that series of that sequence of terms, or this list of terms, can be thought of as a sequence. Okay, so if the limit of the sequence of partial sums converges to L as capital N goes to infinity, in other words, we keep looking at more and more partial sums, more or less like we did here, then we say that our series converges and its limit is L. It's exactly what we did down below. We established that S sub capital N has this general rule to it. So the sequence of partial sums is a sequence following this rule right here. And we took its limit as n goes to infinity, and that limit turned out to be 1. So the limit of that series is 1. So that's our definition of convergence. Okay, so here we're looking at the geometric series. Okay, this is our geometric series. It has a ratio r. It's raised to an nth power. And in some cases, there might be some constant a, some real number times our ratio. Now, in most cases, what we're going to find later on that when the series converges, this is not most cases, this is generally true, when the series converges, this a can be factored out and put in front of this series. All right, so for now, what we'll consider is a equals 1, or basically no a written in there, and we'll just look at the series sum from n equals 0 to infinity, r to the n. Now, next step, we'll write the partial sums down. What we're looking for is a formula for S sub n for this partial sum and to check whether or not its limit as n goes to infinity converges to some limit L to know whether or not this series converges based on our definition. So we write down our first n terms added together. That's r to the 0, r to the 1, r squared, r cubed, plus all the way up to r to the n. Okay. R to the 0, of course, is 1. And we're going to mention that we're looking for a formula for S sub n just to motivate what we do next. But here's our S sub n, S sub capital N, rewritten with 1 as r to the 0. Okay, now it turns out a nice trick for this is to write s sub n plus 1, which is all of s sub n plus r to the n plus 1. Okay, once we add that, so we see that there's a distinction. This is all of this term is just s sub n. So s sub n plus 1 is actually equal to s sub n plus this extra term. So that's one formula for s sub n plus 1 involving s sub n. We have two unknowns essentially. We want a formula for this or this one. It won't matter which one we get because we're going to take the limit as n goes to infinity anyway. So we need another equation involving these two variables or unknowns. So the other thing we realize that if we multiply s sub n by r, this becomes an r squared, r cubed, up to r to the n plus 1. So now these n terms, when they're multiplied by r, match these n terms. So in order to recover all of Sn plus 1, we need to add the extra 1 to it. And that's that right there. So if we do that, we get the second identity down here. We have that S sub n plus 1 is multiply S sub n by r to increase all of these to match these terms, and then add the extra 1 we need to fill in for the last step. So this is the second way in which S sub n and S sub n plus 1 are related. Now we have two equations involving two unknowns that we're interested in. We know r, so r to the n plus 1 is known and r to the n is known, so that's fine. So we want to solve for s sub n. In doing so, we set both of these equations equal to each other because they're both equal to s sub n plus 1. So we've used substitution right away in our system of linear equations here. And we now have that one side is equal to the other. One of the right-hand sides is equal to the other right-hand side. And we can work from here to isolate s sub n. By the time we're done with that, we have that s sub n is 1 minus r to the n plus 1 over 1 minus r. So this is our general rule for one of these series. So this works for a finite geometric series, which we see written below. So if we were working with n equals 0 to capital N, r to the n, then we have a formula out of this for the partial sum. It's 1 minus r to the capital N plus 1 over 1 minus r. Now, if we're working with an infinite series, which is what we're really interested in, we're going to work on the next page, we're going to see when this might converge. But in general, we could evaluate what this is equal to without adding up in terms. If capital N was 100, you really don't want to do all the work to see what that actually is. So this closed formula is really nice to have around. It's just one quick calculation, 1 minus 100 to the capital N plus 1, or sorry, 1 minus whatever r is to the 100 plus 1 over 1 minus whatever r is. So to find that 100th partial sum or 100 terms. Now, when it's infinite, we need to deal with this in a slightly different way. So the question is, does this converge? And if so, when does it converge? So what we look at is the limit. The limit as this partial sum as n tends to infinity. So 1 minus r to the capital N plus 1 over 1 minus r, and that's equal to 1 over 1 minus r whenever the magnitude of r is less than 1. So think about it this way. Maybe it's 1/2. If r is 1/2, we're raising it to increasing powers. 1/2 raised to increasing powers is 1/4, 1/8, 1/16, 1/32. It's getting smaller and smaller, so it's shrinking to 0. In fact, that works for any r value whose magnitude is less than 1. It will shrink to 0. Positive, negative, it won't matter. It's going to approach 0. So that's why we use this highlighted rule off to the side here. When the magnitude or the absolute value of r is strictly less than 1, then this term goes to 0, and our limit is equal to 1 over 1 minus r. So that's our convergence law or rule for the geometric series right here. This series converges, it's equal to 1 over 1 minus r whenever the magnitude of the ratio r is less than 1, strictly less than 1. If r was equal to 1, it'd be a little bit more problematic. Up here, it would seem okay. 1 minus 1 to any power is 1. So we'd have 0 in the numerator. but we'd have 1 minus 1 in the denominator, and that's undefined. So the cutoff is exactly at 1. It does not converge when the magnitude of r is equal to 1. So this is our first main series convergence rule. And it's one to certainly remember. You probably use it so much that you will remember it anyway. Generally, what we'll find later with a series law about summing and multiplying by constants is that if we do have some constant a times our series term and the series converges, in other words, for this geometric series, the magnitude of r is less than 1, well, we can factor a out front. It's times what the series sums to, thanks to it being convergent. So it's a times 1 over 1 minus r, and we get exactly this term right here. So this is what we were overall looking for, and what we'll generally use. So we estimated before that this was probably going to 1/2, or sorry, to 1. We actually kind of did a fairly decent calculation of it without having the definition of partial sums yet. We also did not prove that our sequence S sub n on that previous page, a couple pages ago, was actually equal to that. That can stand to be proven, but the analysis we did was sufficient enough to see where we're headed. This actually proves it once and for all, thanks to the work we did above. So the sum of n equals 0 to infinity of 1/2 to the nth power is 1 over 1 minus the ratio. Notice that this is true because the magnitude of 1/2, or the absolute value of 1/2, is less than 1. So we have 1 over 1 minus 1/2, which is 1/2, or 1 over 1/2, which gives us 2. Now hold up, that seems a little bit off. It's summed to 2. I thought it was supposed to sum to 1. We'll keep track of one piece of information. When n equals 0, we have a 1. We have 1/2 to the 0th power is 1. So our series term, our first series term is 1. What we were missing was that 1 a couple pages ago, and I'll point that out. We did n equals 1, so our first term was 1/2. So the extra 1 added to that is missing here, but it is on the next one, which means that whatever's left for the whole series with n equals 0 here to sum up to 2 means that all of these need to be exactly equal to 1, and they in fact are, as we've shown. So that's it for introducing series and their convergence. To finish this section in the next video, we'll cover telescoping series, the harmonic series, and a rule for divergence. So be sure to check that out to learn more about these series and their analyses.